Okay, so we're here for the last problem on AP Physics vertical motion. This is problem 6. It says, consider the situation. Time 0, there's observer A on the edge of a cliff, throws a ball upward with initial velocity of 30 meters per second. Let me go ahead and start my sketch here. So we've got this cliff, right? Some grass, right? Anyway, and there's an observer here standing on the edge of that cliff, right? Okay. And the observer is going to throw a ball upward with an initial velocity of 30 meters per second. Okay. Meanwhile, all right. Meanwhile, it says that's observer A. Let me go ahead and put a next to him. Observer B, all right. It says is located in a helicopter, which is rising alongside the cliff, right, with a speed of 30 meters per second. At the same time, time t equals 0, at which A throws his ball up, B is passing and releases a ball from his window. So here we go. So all right, we got our helicopter. So your main rotors here. Look at that. Okay, and let's see here. We're going to have observer B here, right? And he's going to go ahead and release a ball reaching out the window. And he's going to release the ball at the same time. Okay? Here. Okay? And he was moving up at 30 meters per second. And so if he's moving up at 30 meters per second, the ball is moving up at 30 meters per second. So when he lets go of the ball is already moving 30 meters per second upward, right? You say, and that's the speed of the helicopter. So the question now says, at that same time, when she throws, he lets go. B simply lets go of the ball without any throwing action. B continues upward in the helicopter at a constant 30 meters per second, no change in its velocity. So that is the situation at the point where they both release their balls. A throwing upward and B moving up and letting go. All right, here we go. Question I. From A's point of view, how does A describe the ball's velocity varying after this? How does he describe their acceleration? Discussed for the entire time from release. You say, what is A going to see? From A's point of view, A is going to see both balls starting with 30 meters per second. Both balls, he says, the only force on them is gravity, which is going to pull down on them and have a downward acceleration. So he'll see both balls do the exact same thing, right? Getting slower, 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 hit a peak, and then fall back down, right? Accelerating, right? Okay, and that's what he's going to see both balls doing, right? Yes, yes? And he'll see the red one do the identical motion, all right? So red will be identical to that. I think we're pretty clear. Okay, let's go to the more interesting question. Part II is from B's point of view. From B's frame of reference, what does he see the balls doing? Well, remember that he is going to continue moving up 30 meters per second. From his point of view, though, as far as he's concerned, he's sitting still, right? From his frame of reference. In your own frame of reference, your speed is 0. Compared to you, the speed at which you're going is 0, right? And so when he lets go of the ball, what will he see the red ball doing? Well, isn't he going to leave it behind? Helicopter B is going to keep going up at 30, right? Going up at 30, 30, at 30, at 30. But this ball is going to be getting slower and slower. From his point of view, he's going to leave it behind. From his point of view, a second later, he'll still be going at 30, but he thinks he's 0, right? He'll see this one, it'll be going up 9.8 meters per second slower. He'll see this ball is going up, if this ball is going up from A's point of view, A sees this ball a second later going up at, what is that, 20.2? But he'll see it being 9.8 less than him. You see what I mean? From his point of view, it's going to look to him like this ball is falling. Do you see that? In a second after that, it'll be 19.6 meters per second less than 30. So it'll be going up from A, you'll see it going up at 19.6 less than 30. He'll see it going up at 10.4 meters per second. But he was going at 30. He'll see it going negative 19.6 from his point of view. Do you see that? As far as he's concerned, it looks exactly like this ball was just dropped. From his point of view, it looks like he's sitting still, and it looks like the ground is moving down at a constant 30, right? And A is going down at a constant 30 from his point of view. But this ball will look like it just started to fall. And this one will look to him like they're doing the same thing. Compared to the helicopter, they're just accelerating down the whole time. Do you see that? Does that make sense to you? Part I says, how does B describe the ball's velocity varying? Right? Okay. Sorry, I just went out of sequence, didn't I? What about when this is at the peak? You know, for A, the peak there, that's when it changes direction, right? And it has a speed of 0 compared to him. But what about from B's point of view? From B's point of view, at time 0, right? It's going at the same speed as him. So from his point of view, from B's point of view, it's sitting still at that first instant. It starts from rest. And then it's just going to be getting slower and slower. It'll look to him like it's falling away. Is there anything special about this spot in his frame of reference? It's not changing direction there or anything from him. It just continues to get 9.8, 9.8, 9.8 meters per second downward every second. To him, it's just in the middle of the fall. There is nothing special about this point in time in this frame of reference. It's not changing direction or doing anything like that. Isn't that interesting? Right? So, yeah, at that point, it just looks to him like it's falling at 30 meters per second at that point where in this frame it's 0, but from his frame, it'll be dropping away at 30. It's just in the middle of the fall. So it's interesting that spots like turning around sort of thing and changing direction, it really just depends on the frame of reference you're looking from, which is kind of cool. Kind of cool. As far as acceleration goes, right, both of them will see these getting slower by 9.8, or have a downward acceleration of 9.8. From his point of view, that just makes the ball get slower as it's going up. From his point of view, it looks like it's getting faster falling down, 9.8 faster each second, right? And he just sees it always dropping way faster and faster and faster from his frame. So it's interesting and noteworthy that if I have these two different frames of reference, both people that aren't accelerating, and that's important, from both their frames of reference, they both would draw the same force diagram for the two balls. They'd both show just one force, gravitational force. They'd both agree F equals ma, same acceleration. They'd agree on all that. They just don't agree on the velocities of the balls. And it's interesting that that turnaround doesn't happen from this guy's frame. It's interesting. Frames of reference we'll talk a little bit more about towards the end of the unit, perhaps. And then at some point, we'll talk about it a lot more at the very end of the year. I'd like to talk to you about Einstein's theory of special relativity, which has to do with motion from different frames of reference. But you can understand it better, believe it or not, once we've gotten to the end of this course and talked about electricity and magnetism. I know it sounds weird that talking about relative motion, that the key to understanding it has to do with electricity and magnetism. Wild, huh? But that's it. At the end of the year, we'll talk about that and why that is. So this is a topic we will come back to. But what's interesting is the takeaway from this is the idea that looking from different frames of reference makes a difference to velocities and displacements, but it doesn't make a difference for accelerations and forces. Okay, and that's problem 6.